Hello everybody, welcome back. In the last video we talked about how when light reflects off of a plane mirror, the law of reflection can be used to determine where the image will be. Those same rules apply if you curve the mirror surface, but the results are different. Let's take a look. First, remember the different types of mirrors. We already talked about a plane mirror, which is just a normal flat mirror, and a mirror which is a plane mirror. Here I'm showing one with the blue side is the reflective side. The black side of the line is the back of the mirror. And so my object here is a pig that's out in front of the mirror. And if you measure the distance of the pig to the mirror, that's called DO in our equations, the distance of the object to the mirror, and then you determine where the image will be found behind the mirror, we always found that the image distance was the same distance as the object distance. It's just that the image was behind the mirror. Also, since the image had no light back there at all, you would not be able to project that image onto a screen, and so we call that a virtual image. The fact that it's right side up compared to the original object, we say that it is erect. So when we compare images to objects, what we'll be looking for is whether the image is erect or not, right side up, whether the image is virtual or real, and whether the image is the same size or not. So let's take a look at a curved mirror. A mirror could be either concave or convexly curved. We'll look at the concave ones first. So let's bring in a mirror, and this time we've curved it. Again, I'm showing the reflective side of the mirror is blue, the back side of the mirror is black. On all my examples here, I'm going to have the mirror facing the same way, so the objects will be on the left. Of course, you know, in real life, the mirror could face any direction, but just for consistency, I'm going to draw mine the same way every time. Now, when you have a curved mirror like this, there's an imaginary line that runs right through the center of the mirror that we call the optical axis, and it's a handy reference point. Any light ray that came in and hit the mirror and it's running right along that optical axis is going to reflect right back over itself. However, if you have a series of rays running parallel to the optical axis like this, when those light rays hit the mirror and reflect, we can go through and construct a normal for every one of these and measure the angle of incidence and measure the angle of reflection. And what we will find is that all those rays end up reflecting back in toward the optical axis. And in fact, if that mirror is very finely made and the curve is parabolic, they will reflect exactly to one point. And we call that point the focal point. And when we talk about concave mirrors, the focal point is very important. We'll usually describe mirrors in terms of their focal length, which is the distance of the focal point to the mirror. And so with the finding the location of an image, it makes a difference whether the object is outside the focal point or whether it's inside the focal point. So let's take a look at these. First, we'll consider a case where the distance of the object is greater than the focal length. So in other words, it's outside the focal point. Then we'll look at a case where an object is inside the focal point. In other words, the distance of the object is less than the focal length. Now, an example of where this kind of mirror is found, since they concentrate or converge light from a very large area down into a very small area, they're concentrating that light. This is the type of thing that you would see in a satellite dish. A satellite dish takes a signal from a satellite which is many thousands of miles out in space, and it collects all the information, all the signal from that satellite, which is spread over a big surface area, and it focuses it down into a very tiny point so it can be strong enough to be detected. So concave mirrors are often used to magnify the strength of light signals. Let's talk about how to find an image in one. We'll start with a case where the distance to the focal, or the distance of the object, is greater than the focal length. So here we've got our mirror, and I put in the focal point, and for my image I'm going to use a candle like we did in the video with the plane mirrors. To find where that image will be, we start off by drawing a light ray, or choosing a light ray that's coming from the object that's running parallel to the optical axis. Now we chose that one on purpose. Remember, with the plane mirror, we could actually choose any light ray, and then we could construct a normal where that ray hits the surface of the mirror, measure the angle of incidence, construct the angle of reflection. But since we're on a curved mirror, it turns out it's much easier, because any light ray that travels parallel to the optical axis, when it bounces off, we know that after we've done all that normal and angle of incidence, angle of reflection stuff, that light ray is going to be bouncing out through the focal point. So any light ray that comes into the mirror parallel to optical axis reflects through the focal point. The inverse of that is also true. Any light ray which comes into the mirror traveling through the focal point, when it reflects off of the mirror, it will go parallel to the optical axis. So for our second light ray, we're going to start at the top of the candle again, but we're going to choose a light ray that travels from the candle into the mirror but passes through the focal point on its way. And when that ray then reflects off the mirror, we know it will be traveling parallel to the optical axis. Notice that those two light rays that were originally together at the top of the candle, they come together again after reflecting. Where those two red reflected rays come together, that is where our image will form. Now remember, we said that anything on the optical axis is going to bounce back right straight on the optical axis. That means on our image of the candle, the bottom of the candle will still be on the optical axis, since the real candle, the bottom of it was on the optical axis. But the top of the candle on the image will be where those two light rays come together. So our image will form right here. Notice that that image is upside down. We say that it is inverted. Now the other thing about this, since those red reflected light rays really do come together, now that's different than it was in the plane mirror. Remember, in the plane mirror they were diverging. They looked like they were spreading apart. They never came together, but there was a point in space where they looked like they were together. These images really come together, and so that image is a real image. If we put a screen right there at that point in space, the image of the candle would be projected and it would show up on that screen. So, when the object is beyond the focal point, our image always turns out to be real and inverted. Let's take a look at it when it's the other way around, when our object distance is smaller than the focal length. In other words, we're going to move our candle inside the focal point. Now when we find the image, the process for finding the location is similar. Again, we start off by picking a light ray that's traveling parallel to the optical axis, because when it reflects off, we know it's going to reflect through the focal point. For our second one, we want to choose a light ray that looks like it originated at the focal point and passed through the very tip of the candle. So it's lined up with the focal point and the tip of the candle. So the blue part of the ray is the incident ray, but when it reflects off the mirror, it will be traveling parallel to the optical axis. Notice those two red reflected light rays are not parallel to each other, and they're not converging. They're spreading apart. So those two rays will never come together. They will never form an image that could be projected on a screen. But if you were out there on the reflective side of the mirror and you were looking at the reflection of the candle, those two light rays look like they originated back here behind the mirror. There is a point in space where it looks like they are together. So at that point, that is where the image that you would see would be located. Notice that it's bigger than the actual original object. Notice also that it cannot be projected on a screen because there's not really any light there. So this image is right side up. So the terminology we use, we say that image is erect. It is virtual because it cannot be projected onto a screen, and it's magnified because it's bigger than the original object. Let's take a look at the last possible situation. What if we have a convex mirror instead? A convex mirror is one where the reflective side is bulged out rather than caved in. It still has an optical axis just like we had before, but this time if we imagine several light rays coming in that are all traveling parallel to the optical axis, if we construct normals and measure angles of incidences and angles of reflection, those light rays, when they reflect, they're all going to be spreading out like this. So any light that bounces off of a convex mirror is going to be diverged. It will be spread out. So sometimes we call this type of mirror a diverging mirror. And when we think about a focal point, remember in the concave mirror, the light really did come together at a focal point. You could put that focal point, if we held a piece of paper there, the focal point, the dot of light would show up on it. But here the light is being spread out. It really doesn't come together anywhere. But if you trace those reflected light rays back to where it looks like they originated, there is a point in space back behind the mirror where those rays appear to have come from. So the focal point in this case is virtual. If we were dealing with it mathematically, we would say the focal length here would be negative because the focal point is back behind the mirror. So to find an image, let's again bring in our object, and we'll use the candle just like we did before. And just like we did in the last example, we'll start off by taking a light ray in that runs parallel to the optical axis. Now when it hits the mirror, we know it's going to bounce up and away because it will be diverged, and it will travel off in a direction that looks like it's coming from the focal point. So if we had a ruler, we would line it up, and we'd line up the focal point with the point where the incident ray hits the mirror, and then our reflected ray is going to be traveling along that line straight out away from the focal point. Our second light ray, we aim it in from the top of the candle right toward the focal point, but of course it doesn't make it there because it runs into the mirror. So the incoming ray, or the incident ray, would actually stop right at this point. Now when that ray hits the mirror, however, it will bounce out and it will be running parallel to the optical axis. So our two red reflected rays are the ones that will help us figure out about the image. Notice again they are diverging. They will never come together, so the image is going to be a virtual image. If we were looking at that curved mirror, those two rays would look like they were coming from back here. And where those two rays cross, that is where our image would form. And notice this time that it's going to be much smaller than the original object. But it's right side up, it's virtual, and it is reduced in size. Now, this type of mirror actually is used fairly commonly. You may well have seen them like on the side of a car. Well, they'll have a mirror curved this way, and then they usually have a little warning on it that says, "Caution, images appeared through this mirror are closer than they appear to be." Because this mirror makes the thing look smaller, the image is smaller than it normally would be through a plane mirror, our brain interprets that as saying it's farther away. And so that's why they put that little warning on there. This shape of mirror gives us a very wide field of view, but everything we see in it is a little bit smaller than what we would normally expect.